Hello students and warm greetings of the day. In this lecture we are going to study how to calculate the probabilities of different events that occur in our day-to-day life. But why are we so interested in studying this topic? This is because it is an important tool that helps us to make decisions. It gives us a better understanding of how to choose between options. It is applied in risk assessment, in trading on commodity markets where the analyst predicts the prices of the commodities in the futures market. Reliability theory is used in product designing to reduce the probability of failure. Probability is used in information theory and signal processing. It is used in studying the models of population growth and communication networks. Thus we see that there are diverse applications of probability. So let's discover this fascinating world of probability which enable people to be better decision makers. So let's begin. Now before we define this term probability, let us try to see an example. If I say that it may rain today, now does it mean for surety that it will rain today? No, it's not for sure. It may or it may not rain. Now one can say there's a 50-50 chance of raining or not raining. Now if I say it's a sunny day, then may it rain? Yes, definitely it can rain. The weather can change and it can rain again. The chances of raining become low. So it might be a 25-75% chance of raining and not raining. Thus the event of raining is not a certain event. It may or it may not happen. Now, what is probability? Probability, when defined in the simplest way, is a chance of occurring of a certain event when expressed quantitatively. That is, probability is a quantitative measure of the certainty. Now let's consider the same event, that it's about to rain. Now it can rain and it cannot rain today. Now the quantitative measure of the certainty of raining is known as probability of raining, and the quantitative measure of the certainty of not raining is again the probability of not raining. So once again we can say that probability is the quantitative measure of the certainty of a certain event to happen. So what is probability? Probability is the mathematical measurement of the certainty of any event to happen or not happen. Now before we further go into this chapter, there's some important things to remember. The first is dice. Now what is a dice? A die is a small cube used in games of chance. I'm really very sure you must have played Snakes and Ladder, Monopoly and many other games that use a die. So a dice is a small cube used in games of chance. The outcome of throwing a die is the number of dots on its uppermost face. Now if I consider this die, there are 5 dots on the uppermost surface of this dice. So the outcome is 5. For this dice the outcome is 2. An ace on a die means 1 dot. So if 1 dot appears on the uppermost surface, then it is known as an ace. So a die is a small cube used in the games of chance. Now we are going to use dice very frequently in this chapter. The second is playing cards. Now everyone knows what are playing cards. A pack of playing cards has 52 cards divided into 4 suits. That is the spades, clubs, hearts and diamonds. So this is an ace of spade, this is a king of heart, this is a queen of spade again, this is a jack of diamond. And there's also one suit known as the club. Thus a pack of playing cards has 52 cards and these are divided into 4 suits: spades, clubs, hearts and diamonds. Now each suit has got 13 cards. 9 cards numbered 2 to 10, an ace, a king, a queen and a jack or knave. So we can say each suit has got 13 cards. 9 cards are the numbered cards, that is from 2 to 10, and the remaining 4 cards are an ace, a king, a queen and a jack. Spades and clubs are black faced cards while hearts and diamonds are red faced cards. The kings, queens and jacks are called the court cards or the face cards. So jack, queen and king are called as the court cards. Thus once again a pack of 52 cards has got 4 suits, that is spades, clubs, hearts and diamonds. Each suit has got 13 cards, 9 cards are numbered and the remaining 4 are ace, king, queen and a jack. Spades and clubs are the black face cards while hearts and diamonds are the red face cards. And finally the kings, queens and the jacks are called as the court cards. So there are some very important terms and concepts which we need to understand. The first is random experiment. Now it is an experiment whose outcome cannot be predicted with certainty. As the word suggests, it is a random experiment whose outcome cannot be predicted with certainty. We cannot be sure of the outcome of that experiment. For example, throwing an unbiased dice. Now if I throw a dice, the outcomes that are possible are 1, 2, 5, 6, 3 and 4. Now I cannot predict which number is going to appear on the dice. So it is a random experiment. Tossing of a coin. Now again this is a random experiment because we do not know for sure whether it's going to be heads or it's going to be tails. Another example could be drawing or picking a card from a set of packed cards. So these all are examples of a random experiment. The second is sample space and sample points. So the set of all possible outcomes of a random experiment is called as the sample space, and it is denoted by S. Now every possible outcome, that is every element of this set, is a sample point. So we can say that sample space is the set of all the possible outcomes of any random experiment. This set is known as a sample space, and every possible outcome, that is every element in this set, is called as a sample point. For example, if I toss a coin, now the possible sample space would be heads or tails. So it could either appear a head or it could appear a tail. So head and tail is the sample space. Anything beyond heads and tails is not possible. So S is H, T, where H is head and T is tail. Now when two coins are tossed simultaneously, then what are the outcomes? Either it could appear heads, or it could be head, tail, or it could be tail, head, or it could be tail, tail. So these are the four possible outcomes, and the set of all these four outcomes is known as the sample space. Now each of these is a sample point. That is, this is an element, this is an element, this is an element, and this is an element of the sample space S. So the set of all possible outcomes of a random experiment is known as the sample space and is denoted by S, and every possible outcome of such a set is known as a sample point. The third is trial. The performance of an experiment is called as a trial, and the outcomes are called as the cases. The number of times the experiment is repeated is called as the number of trials. So if I toss a coin, now this is the performance of an experiment, that is tossing of a coin, and so it is called as a trial. And if it is a head or it is a tail, this is called as the case. The case one could be, it could appear a head or it could appear a tail. So I'm sure the distinction between a trial and a case is clear. Now I may toss a coin twice, thrice, 4 times, 10 times, 20 times and so on. And so the number of times the experiment is repeated is called as the number of trials. The fourth is event. Now what is an event? The possible outcomes of a random experiment are termed as events, and it is a subset of a sample space. For example, when a coin is tossed, the outcome of getting a head or tail is an event. Event is nothing but the possible outcomes of any random experiment. So if we toss a coin, it could appear a head or it could appear a tail. So head or tail is an event. Event 1 could be appearance of head, and event 2 could be appearance of tail. Now the bifurcations of events could be simple events, compound events, equally likely events, independent events, mutually exclusive events, exhaustive events. One by one we are going to see different kinds of events. The first is a simple event. Now in the case of simple events, we consider the probability of happening or not happening of single events. So we consider a single event and we try to consider the probability of happening of that event or not happening of that event. So for example, if I say that we are interested in finding out the probability of drawing an ace from a pack of cards. So drawing of an ace from a pack of cards is a simple event. The second is compound event. Now in the case of compound event, we consider the joint occurrence of 2 or more events. Earlier in the simple event, we considered only a single event and we were interested in calculating the probability of occurrence of that single event. But in compound events, we consider the joint occurrence of 2 or more events. For example, the occurrence of an odd number when a dice is thrown. Now if I say that I am interested in knowing the occurrence of an odd number when a dice is thrown, possible outcomes are 1, 2, 3, 4, 5, 6. And out of these possible outcomes, 1, 3 and 5 are the instances when an odd number is occurring. So this set 1, 3, 5 is a compound event. The third type of event is equally likely events. The events are said to be equally likely if there is no reason to expect any one event in preference to other. Thus equally likely events mean outcome is likely to occur as any other outcome. So we say that there are two events and there is no such reason to expect the occurrence of one event in preference to the other event. Then such a case is known as equally likely event. For example, if I throw an unbiased dice, then in throwing such a die, all the 6 faces are equally likely to occur. That is, it may appear a 1, a 2, a 3, a 4, a 5 or a 6. That is to say, there is no such reason to expect 1 or 2 or 3 in preference to the other numbers. Thus all these 6 faces are equally likely to occur. So this is an equally likely event. Another example could be if I toss a coin, then it may appear a head or it may appear a tail. Again, these are equally likely events. The next is independent events. The two events are said to be independent if the occurrence of one does not depend on the occurrence of the other. So as the word suggests, independent events are such events in which the occurrence of one does not depend on the occurrence of the other. Now we are going to study independent events in detail in later part. What are mutually exclusive events? In an experiment, if the occurrence of an event precludes or rules out the happening of all other events in the same experiment, then such events are known as mutually exclusive events. That is to say, if we are performing an experiment, then if one particular event occurs, then all other events are not going to occur. So the occurrence of any one event rules out the happening of all other events in the same experiment. If we say that E1, E2, E3 and so on up to En are mutually exclusive events, then E1 intersection E2 intersection E3 and so on up to the intersection of En would be equal to 5. That is a null set. These are mutually exclusive events, then the intersection of these events is equal to 0 or a null set. The next is exhaustive events. What are exhaustive events? It is a total number of all possible outcomes of any trial. So the total number of all the possible outcomes of any trial or any such experiment is known as exhaustive events. For example, when a coin is tossed, either head or tail may turn up, and therefore there are two exhaustive cases. If two coins are tossed simultaneously, then the possible outcomes are head, head tail, tail head, tail tail, and so this would be equal to 2 square. So there are 4 possible outcomes. If 3 coins are tossed simultaneously, then the possible outcomes are head head head, head head tail, head tail head, tail head head, tail tail head, head tail tail, tail head tail, and tail tail tail, and this would be equal to 2q. That is, there are 8 possible outcomes for this experiment. Similarly, when 3 dice are thrown simultaneously, then the possible outcomes are 6q. And so exhaustive events are nothing but they are the total number of all possible outcomes of any trial. Now let us try to understand the algebra of events. Now if we say that A and B are two events and these two events are associated with the sample space S, then we can have this sample space, that is S. We can have an event A and we can have another event B. Now A union B is the event that either A or B occur. So this is A union B. Now A union B means that either A or B or both of them occur. The second is A intersection B is the event that A and B both occur simultaneously. So this event, that is A intersection B, represents the occurrence of A and B simultaneously. Now A complement is the event that A does not occur. So all this space which does not include the event A is known as A complement. So we can say that A plus A complement would be equal to the sample space S. And the fourth is A complement intersection B complement mean none of the events A and B occur. Now A union B means that either A or B or both of them occur. A intersection B means the event that A and B both occur simultaneously. A complement is the event that A does not occur, and A complement intersection B complement represents that none of the events A and B occur. Now let us consider an example. In a single throw of die, let A be the event of getting an odd number and B is the event of getting a number greater than 2. Then A would be the set 1, 3, 5 as these are odd numbers, and B would be 3, 4, 5, 6, because these are the numbers greater than 2. Now we have to find A union B. Therefore A union B would be equal to 1, 3, 4, 5 and 6. That is the event of getting an odd number or a number greater than 2. So we see here that the event of getting an odd number or a number greater than 2 is A union B, and which is equal to the set 1, 3, 4, 5, 6 in this case. The second is A intersection B. This would be equal to 3, 5, as these are the common points of these two sets. So A intersection B would be 3, 5, and so we can say that this is the event of getting an odd number greater than 2. So the event of getting an odd number which is greater than 2 would be 3, 5. Now we see that A is the set 1, 3, 5. Therefore A complement would be 2, 4, 6. That is, these are the elements of S which are not in A, or the event of not getting an odd number. If we are interested in finding the event of not getting an odd number, then that would be equal to A complement, and which is equal to 2, 4, 6. And so these are the elements of S which are not in the set A. The fourth is A complement intersection B complement. Now this would be equal to 2. That is the event of neither getting an odd number nor a number greater than 2. So thus A complement intersection B complement is equal to the single element 2. So this was an example to understand the algebra of events. Now what are mutually exclusive and exhaustive events? Now we have earlier seen that a mutually exclusive event is such that if one event is happening, it rules out the possibility of happening of other events. If we say that E1, E2 up to En are mutually exclusive and exhaustive events, then the first condition is E1 union E2 union E3 and so on up to En would be equal to S. Your S is the sample space, and Ei intersection Ej is equal to phi. So this is the property of a mutually exclusive event, and this is the property of exhaustive event. So the combined mutually exclusive and exhaustive events would be such that E1 union E2 union E3 and so on up to En would be equal to S, and the intersection of any of two events would always be equal to phi. For example, if we consider a single throw of a die, then if we say that A is the event of getting an even number and B is an event of getting an odd number, then A would be equal to 2, 4, 6 as these are even numbers, and B would be equal to 1, 3, 5 and these are odd numbers. Now A intersection B would be phi, and A union B would be equal to 1, 2, 3, 4, 5, 6, and this is equal to the sample space S. This is the set of all the possible outcomes. So we see that it satisfies this condition and it satisfies this condition. So A and B are mutually exclusive and exhaustive events. So let's consider an example. Two dice are thrown and the sum of the numbers which come up on the dice are noted. Let us consider the following events. A is the sum is even, B is sum is a multiple of 3, C is sum is less than 4, and D is sum is greater than 11. So which pair of these are mutually exclusive? So in this problem we have been given that two dice are thrown and the sum of the numbers which come up are noted. Then we have to consider the following events. A is the event that is the sum is even, B is the event that sum is a multiple of 3, C is the event that the sum is less than 4, and D is the event that the sum is greater than 11. Now we have to check which pairs are mutually exclusive events. Now we see that there are 6 cross 6, that is equal to 36 elements in the sample space. So there are in all 36 elements in sample space, because for the first dice there are 6 possible ways, and for the second dice there are again 6 possible ways. So in all there would be 6 cross 6, which is equal to 36 elements in the sample space. Now we see that A is the event that the sum is even. So it means that we have to consider those ordered pairs x comma y in which x plus y is even. So A would be equal to 1, 1, 2, 2, 1, 3, 1, 5, 2, 4, 2, 6, 3, 1, 3, 3, 3, 5, 4, 2, 4, 4, 4, 6, 5, 1, 5, 3, 5, 5, 6, 2, 6, 4 and 6, 6. So these are the sample points that belong to the set A, which is the sum should be even. Now B is the sum should be a multiple of 3. Now we see that the sum of these two numbers should be a multiple of 3. Now the multiples of 3 could be 3, 6, 9 and 12. The maximum could be 12. So the sample points for set B would be 1, 2, 2, 1, 1, 5, 5, 1, 3, 3, 2, 4, 4, 2, 3, 6, 6, 3, 4, 5, 5, 4 and 6, 6. Now C is the event that the sum is less than 4. For sum less than 4, the sum could be 2 and 3. Therefore the sample points are 1, 1, 2, 1 and 1, 2 for the set C. And for the set D, we see that the sum should be greater than 11. Now the only number that is greater than 11 is 12. So the sum has to be equal to 12, and that is only possible for a case which is 6, 6. That is 6 appears on the first dice and 6 again appears on the second dice. So we see that these are the sample points for set A, set B, set C and set D. Now we find that A intersection B would be 1, 5, 2, 4, 3, 3, 4, 2, 5, 1 and 6, 6. And so we see that these are not mutually exclusive events. This is because if A and B were to be mutually exclusive events, then A intersection B should be equal to 5. Now similarly, if we see A intersection C, then this would again be not equal to 5. A intersection D would not be equal to 5. B intersection C would not be equal to 5. B intersection D would not be equal to 5. But C intersection D is equal to 5. Thus we can say that C and D are mutually exclusive events. These are mutually exclusive events, but these are not exhaustive events. So we can say that C and D are just mutually exclusive events because C intersection D is equal to 5. Till now we have seen different types of events. Now let's come to the main part of this lecture, which is calculating the probability of an event. Now we see that probability is the way of quantifying certainty of an event to happen or not to happen. But now let's see how we actually calculate probability of an event. Probability of an event is denoted by P of A and is defined as P of A equal to number of cases favorable to A divided by the number of possible outcomes. So we can say that the probability of event A happening is equal to the number of cases which are favorable to A divided by the total number of possible outcomes. Now if an event A can happen in m number of ways and it fails, that is, it does not happen in n number of ways, and each of these m plus n ways is equally likely to occur, then the probability of happening of the event A, also called as the success of A, is given by P of A equal to m divided by m plus n. So if we say that there are m number of ways in which A can happen and there are n number of ways in which A cannot happen, then the probability of happening of A is equal to m divided by m plus n. Similarly, the probability of non-occurrence of A, also called as a failure of A, is given by P of A complement, which is equal to n divided by m plus n. Here we are trying to calculate the probability of non-occurrence of A. So the number of ways which are favorable to the non-occurrence of A is equal to n, because we have seen that there are n number of ways in which A cannot happen. So n divided by m plus n, which are the total number of ways, would be equal to P of A complement, that is the probability of non-occurrence of A, that would be equal to n divided by m plus n. Now if the probability of happening of certain event is denoted by P and that of not happening by Q, then P plus Q would be equal to m divided by m plus n divided by m plus n, and that would be equal to 1. Thus the probability of happening of an event plus the probability of not happening of that event is equal to 1. Now we see that your P and Q are such that P and Q both are greater or equal to 0 and less than equal to 1. Now we see that the probability of happening of A, which is denoted by P, and the probability of not happening of A, which is denoted by Q, are such that P and Q are greater or equal to 0 and less than equal to 1. Thus P and Q lie in this interval. Now if I say that P is equal to 1, then the event is certain to occur. Now if P is equal to 0, then the event is impossible, that is, the event cannot occur, because Q would be equal to 1 in that case, and Q means the probability of non-occurrence of event A, and so event A would be impossible to occur. For example, if we are interested in calculating the probability of throwing 8 with a single die, then we know that it cannot happen because the maximum number which can appear on a die is 6. So the probability of throwing 8 with a single die is equal to 0. Now probability as defined above is sometimes called as priori probability. That is, it is determined beforehand or before the actual trials are made. So it means that probability is something which is calculated or determined before the actual trials are made, because once the trials are made, we can definitely know the final outcome. For example, if I toss a coin, now there are two possible outcomes, a head or a tail. Now both are equally likely, so the probability is 1 by 2. That is, either a head could appear or a tail could appear. But once I have tossed it, for certain I know whether it has appeared a head or a tail. So probability is something which we actually try to calculate or determine before actually tossing the coin. So that's why it is also called as priori probability. Once again, let's see a solved example. What is the probability of drawing a red face card from a well shuffled deck of 52 cards? So in this problem, we have to calculate the probability of drawing a red face card from a well shuffled deck of 52 cards. So we see that there are 12 face cards in a deck, out of which 6 are red faced cards. Now the face cards are King, Queen and Jack, and there are 4 suits, so 4 into 3 would be equal to 12, and so we see that there are 12 face cards. Now out of these 12 face cards, there are 6 red face cards. Now among the 4 suits, there are 2 suits which are red in color. There are heart and diamond, and so in all there are 6 red faced cards. So the probability of a red face card would be equal to 6 divided by 52, as the total number of cards in a deck is 52. So the probability of a red face card is equal to 6 by 52, which is equal to 3 by 26. The next topic is odds of an event. Now suppose there are m outcomes favorable to a certain event and n outcomes unfavorable to the event in a sample space. Then we say that odds in favor of the event is equal to the number of favorable outcomes divided by the number of unfavorable outcomes. So odds in favor of the event would be equal to m divided by n, which is m is the number of outcomes which are favorable to a certain event, and n are the number of outcomes that are unfavorable to the event. So m by n would denote the odd in favor of the event. Similarly, the odds against the event would be equal to number of unfavorable outcomes divided by the number of favorable outcomes. That is, it is the inverse of odds in favor. So odds against the event would be number of unfavorable outcomes divided by the number of favorable outcomes, and which is equal to n by m. Now if we say that odds in favor of an event are A is to B, then the probability of happening of event A would be equal to P of A, which is equal to A divided by A plus B. Similarly, the probability of not happening of event A would be equal to P of A complement, and which would be equal to B divided by A plus B. So we can say that if odds in the favor of an event are A is to B, that is, it is a ratio of number of phase which are favorable to A divided by the ratio of phase which are unfavorable to A. So in this case, the probability of happening of event A would be equal to P of A, and which is equal to A divided by A plus B. And the probability of not happening of event A is equal to P of A complement, and which is equal to B divided by A plus B. Similarly, if we say that the odds against happening of an event are A is to B, then the probability of happening of event A would be equal to B by A plus B, and the probability of not happening of event A is equal to P of A complement, which is equal to A divided by A plus B. So based on the above concept, let's try to see an example. What are the odds in favor of getting a 3 in a single throw of die? And what are the odds against getting a 3 in a single throw of die? So we are throwing a die, and we have to calculate the odds in favor of getting a 3 in a single throw, and in the second part we have to calculate the odds against getting a 3 in a single throw of die. So we see that there is only one outcome favorable to the event of getting a 3, and the rest 5 outcomes are unfavorable. So the total possible number of outcomes are 6, because there are 6 numbers which can appear on the uppermost surface of the die. Now we see that there's only one way of getting 3, and the rest 5 numbers are the number of ways in which we cannot get a 3. So odds in favor of getting a 3 would be number of favorable outcomes divided by the number of unfavorable outcomes. Number of favorable outcomes are 1 and the number of unfavorable outcomes are 5. So odds in favor of getting a 3 would be equal to 1 by 5. Similarly, odds against getting a 3 would be number of unfavorable outcomes divided by the number of favorable outcomes, and which are equal to 5 divided by 1. Thus the odds in favor of getting a 3 are equal to 1 by 5 and odds against getting a 3 are 5 by 1. Let's see one more example. If the odds in favor of an event are 4 to 5, that is 4 by 5, then find the probability that it will occur. So in this case we have been given that odds in favor of an event are 4 is to 5, and we have to find the probability that it will occur. So given that odds in favor of the event are 4 by 5, thus PA by 1 minus PA would be equal to 4 by 5, as PA would be the probability of happening of A and 1 minus PA is the probability of not happening of A. So PA by 1 minus PA would be equal to 4 by 5. From this we get 4 times 1 minus PA equal to 5 times P of A, or P of A equal to 4 by 9. Thus the probability that the event A will occur is equal to 4 by 9. Now let's look at some of the fundamental theorems on probability. The first theorem is, in a random experiment, if S is a sample space and E is an event, then the probability of any event is greater or equal to 0. Probability of S complement is equal to 0, and the probability of S is equal to 1, where S is the sample space and E is any event. Now it follows that the probability of occurrence of an event is always non-negative, that is P of E is greater or equal to 0. The probability of occurrence of an impossible event is equal to 0, that is P of S complement is equal to 0, and the probability of occurrence of a sure event is 1, therefore P of S would be equal to 1. The second theorem is, if E and F are mutually exclusive events, then the probability of E intersection F would be equal to 0, and P of E union F would be equal to P of E plus P of F, because P of E intersection F would be equal to 0. Thus, if E and F are mutually exclusive events, then the probability of intersection of E and F would be equal to 0, and the probability of E union F would be equal to P of E plus P of F. Now if we say that E1, E2 and so on up to Ek are mutually exclusive events, then the probability of E1 union E2 union E3 and so on up to Ek would be equal to P of E1 plus P of E2 plus P of E3 and so on up to P of Ek. Thus this is the second theorem on probability. Theorem number 3 is, if E and F are two mutually exclusive and exhaustive events, then P of E plus P of F would be equal to 1, as the probability of E intersection F would be equal to 0, and as E and F are mutually exclusive events, therefore this probability would be equal to P of S, which is the sample space, and that is equal to 1. Thus P of E plus P of F would be equal to 1. The next theorem is, let E be any event and E complement be its complementary event, then P of E complement is equal to 1 minus P of E. So if E is any event and E complement is the event that E does not occur, then the probability of E complement is equal to 1 minus P of E. Theorem number 5 is, for any two events E and F, P of E minus F is equal to P of E minus P of E intersection F. So for any two events E and F, probability of E minus F would be equal to probability of E minus the probability of E intersection F. Theorem number 6 is the addition theorem, and that is a general theorem for any two events. So for any two events E and F, the probability of E union F is equal to the probability of E plus probability of F minus the probability of E intersection F. This is known as the addition theorem. Now if E intersection F is equal to 0, then probability of E union F would be equal to P of E plus P of F. So for mutually exclusive events, we get P of E union F equal to P of E plus P of F. Now we may express the above result as this, because E union F would be equal to E or F. The probability of E union F is nothing but the probability of E or F event to take place. That would be equal to P of E plus P of F minus this is nothing but the probability of E and F occurring simultaneously. So this is P of E and F. Thus we can say that the probability of E or F to occur is equal to the probability of E plus the probability of F minus the probability of E and F to occur simultaneously. The next theorem is the very basic one, that is, if E is an event associated with a random experiment, then the probability of E to occur is greater or equal to 0 and less than equal to 1. So the maximum value of P of E is equal to 1 when E is a sure event to occur, and is equal to 0 when E is an impossible event. So in general, if E is any event, then probability of P of E is greater or equal to 0 and less than equal to 1. The next theorem is the general form of addition theorem. Earlier we have seen the addition theorem for two events. Now if we have got multiple events, then the probability of E1 union E2 union E3 and so on up to En is equal to the summation of P of Ei, where I varies from 1 to n, minus the summation of P of Ei intersection Ej, where I is less than j, plus the summation of P of Ei intersection Ej intersection Ek, where I is less than j, which is less than k, minus and so on up to minus 1 to the power of n into P of E1 intersection E2 intersection E3 and so on up to En. Thus this is the general form of addition for any number of events. Now these were some of the very basics and fundamental theorems on probability which you need to remember. So let us see a solved example. A card is drawn at random from a well-shuffled pack of 52 cards. Find the probability of getting, first is a jack or a queen or a king, and the second is a two of heart or diamond. So in this problem we have been given that a card is drawn from a well-shuffled pack of 52 cards. So we have to find the probability of, first is getting a jack or a queen or a king, and the second is a two of heart or a diamond. So let's see the solution of this. In a pack of 52 cards we have 4 jacks, 4 queens and 4 kings. Now clearly a jack and a queen and a king are mutually exclusive events. So the probability of a jack would be 4c1 divided by 52c1, as we have got 4 jacks. So this would be equal to 4 by 52, and which is equal to 1 by 13. Similarly, the probability of a queen would be equal to 4c1 by 52c1, and this is equal to 1 by 13. And similarly, the probability of a king is 1 by 13. Therefore, by the addition theorem of probability, we get P of jack or a king or a queen is equal to the probability of a jack plus the probability of a queen plus the probability of a king, and that is equal to 1 by 13 plus 1 by 13 plus 1 by 13, and that is equal to 3 by 13. Thus we can say that the probability of drawing a jack or a queen or a king from a well shuffled pack of 52 cards is equal to 3 by 13. For the second part, we have to find the probability of drawing a 2 of heart or a 2 of diamond. Now this would be equal to the probability of 2 of a heart plus the probability of 2 of diamond. Now the probability of this part is 1 by 52 and the probability of this is 1 by 52, as we know that there's only one 2 of heart and there's only one 2 of diamond. So this would be equal to 1 by 26. Thus we can say that the probability of drawing a 2 of heart or a 2 of diamond from a well shuffled pack of 52 cards is equal to 1 by 26. Let's see one more example. Find the probability of getting a sum of 7 or 11 in a simultaneous throw of 2 dice. So in this problem we are throwing 2 dice simultaneously and we have to find the probability of getting a sum of 7 or 11. So now we know that when 2 dice are thrown, then we can have 36 possible outcomes. How? There are 6 numbers that can appear on the first dice, and similarly there are 6 numbers that can appear on the second dice. So 6 into 6 is equal to 36, and so we can say that 36 are the total possible outcomes. Now we have to obtain a sum of 7. Now this can be done by 1 plus 6 equal to 7, 2 plus 5 equal to 7, 3 plus 4 equal to 7, 4 plus 3 equal to 7, 5 plus 2 equal to 7, and 6 plus 1 equal to 7. So we see that there are 6 favorable cases, and they could be written as 1, 6, 2, 5, 3, 4, 4, 3, 5, 2, and 6, 1. So the probability of a sum of 7 would be equal to 6 by 36, and which is equal to 1 by 6. Now we have to find out the favorable cases for getting a sum of 11, and these cases are 5, 6 and 6, 5. So the sum of 11 could be obtained in 2 ways, and thus the probability of getting a sum of 11 is equal to 2 by 36, which is equal to 1 by 18. Now the events that a sum of 7 is obtained and a sum of 11 is obtained are 2 mutually exclusive events, because if we obtain a sum of 7, we cannot obtain a sum of 11, and vice versa. So the probability of a sum of 7 or 11 would be equal to the probability of a sum of 7 plus the probability of a sum of 11. Now this is equal to 1 by 6, and this is equal to 1 by 18. So 1 by 6 plus 1 by 18 is equal to 4 by 18, and which is equal to 2 by 9. Thus the probability of getting a sum of 7 or 11 in a single throw of 2 dice is equal to 2 by 9. Let's see one more example. From a well-shuffled pack of 52 cards, a card is drawn at random. Find the probability that it is either a heart or a queen. So in this problem, again we have been given a well-shuffled pack of 52 cards, and we have to draw a card. But we have to find the probability that it is either a heart or a queen. Now let us say that E is the event of getting a heart card, and F is the event of getting a queen card. Now we know that there are 13 heart cards in a pack of cards, so the probability of E would be equal to 13 by 52. Similarly, we know that there are 4 queens in a pack of cards, so P of F would be equal to 4 by 52. Also we see that there is a 1 queen card which is of the heart. Probability of E intersection F would be equal to 1 by 52. Now the required probability would be equal to the probability of E union F, which is equal to P of E plus P of F minus P of E intersection F. This is equal to 13 by 52, this is equal to 4 by 52, and this is equal to 1 by 52. And so this would be equal to 16 by 52, which is equal to 4 by 13. Thus the probability of getting a heart card or a queen card is equal to 4 by 13. The very next kind of probability is the conditional probability. Now often it is required to find the probability of an event B under the condition that an event A occurs. So this is different from the previous probabilities, that here we have to find the probability of event B under the condition that an event A has already occurred. So this kind of new probability is called as the conditional probability of B given A, and is denoted by probability of B by A. Now here we see that this represents the probability of B given that A has already occurred. So here A is another event which has already occurred, and taking that into account, we calculate the probability of the event B. So such kind of probability is called as the conditional probability, and it depends on the probability of A. So in this case, A serves as the new or the reduced sample space, and the probability is the fraction of that part of set A which corresponds to A intersection B. So in this case, we see that A serves as the new sample space, and the probability is the fraction of that part of set A which corresponds to A intersection B. Now let's try to understand this. Now let us say that this is the sample space S. Now this is any event A, this represents event B, and this represents A intersection B. Now this common portion is represented by A intersection B. So probability of B by A would be equal to the probability of A intersection B divided by P of A. Here P of A is not equal to 0. So in this conditional probability, we see that this sample space gets reduced to this sample space. Now A becomes the reduced sample space, and this portion is what we are interested in. So that's why P of A intersection B divided by the sample space, which is A, becomes the conditional probability, or P of B by A is equal to P of A intersection B divided by P of A. Similarly, we can say that the conditional probability of A given B is P of A by B equal to the probability of A intersection B divided by P of B. Here B becomes the sample space, and P of B should not be equal to 0. Thus this is the formula for conditional probability. The next is independent events. Now what are independent events? We have seen that two events are said to be independent if the occurrence of one does not depend on the occurrence of other. As the word suggests, these events are independent. They do not depend on the occurrence of one another. For example, in a simultaneous throw of two coins, getting a head on the first coin and getting a tail on the second coin are independent events. Why? Because we can get a head on the first coin irrespective of whether we get a tail or a head on the second coin. Thus, getting a head or a tail in a coin are two independent events, and so when we simultaneously throw two coins, getting a head on the first coin is independent of getting a tail on the second coin, and hence these are independent events. Similarly, if I say that when a card is drawn from a pack of well shuffled cards and replaced before the second card is drawn, then the result of the second draw is independent of the first draw. So if we have a pack of cards and we draw a card from this pack of well shuffled cards, now after that I have replaced it with the same card and again a second draw is made. Now this second draw would be independent of the first draw, and so we can say that the result of the second draw is independent of the first draw. Thus finally, once again we can say that independent events are said to be independent if the occurrence of one does not depend on the occurrence of other. So from this we get theorem number 9. If A and B are two independent events, then the probability of A and B, that is A intersection B, is equal to P of A multiplied by P of B. That is, the probability of A intersection B is equal to the product of the probabilities A and B. So based on this, let's try to see a solved example. Arun and Tarun appear for an interview for two vacancies. The probability of Arun's selection is 1 by 3 and that of Tarun's selection is 1 by 5. Find the probability that the first is only one of them is selected and second is none of them is selected. So in this problem we have been given that there are two persons, Arun and Tarun, and they appear for an interview for two vacancies. Now the probability of Arun's selection is 1 by 3 and that of Tarun's selection is 1 by 5. We have to find the probability that the first is only one of them is selected and second is none of them is selected. Now let us say that A represents the event that Arun is selected and B represents the event that Tarun is selected. So the probability of A is equal to 1 by 3 and the probability of B is equal to 1 by 5. Here this represents that Arun is selected and this represents the probability that Tarun is selected. Now we see that there are two vacancies and for which Arun and Tarun are applying. So their selection is independent of each other's selection. Thus we can say that A and not B are independent events. Also not A and not B are independent and B and not A are independent as they are applying for two vacancies. Now the first is the probability of only one of them is selected. Now this can happen only if Arun is selected and Tarun is not selected, or Tarun is selected and Arun is not selected. Thus this would be equal to P of A into P of not B plus P of B into P of not A. Now this is equal to 1 by 3 and this is equal to 1 minus 1 by 5. Similarly, this is equal to 1 by 5 and this is equal to 1 minus 1 by 3. Thus this would be equal to 1 by 3 into 4 by 5 plus 1 by 5 into 2 by 3, and thus this gets reduced to 2 by 5. Thus the final probability of only one of them being selected is equal to 2 by 5. In the second part, we have to calculate the probability that none of them is being selected. So this can happen when both Arun and Tarun are not selected. So this would be equal to P of not A into P of not B, as these are independent events, and so this would be equal to 1 minus 1 by 3 into 1 minus 1 by 5. This would be equal to 2 by 3 into 4 by 5, which is equal to 8 by 15. Thus the probability of none of them being selected is equal to 8 by 15. Let's see again a solved example. An instructor has a question bank consisting of 300 easy true and false questions, 200 difficult true and false questions, 500 easy multiple choice questions and 400 difficult multiple choice questions. If a question is selected, what is the probability that it will be an easy question given that it is a multiple choice question? So in this problem we have been given that there is a question bank consisting of 300 easy true false questions, 200 difficult true false questions, 500 easy multiple choice questions and 400 difficult multiple choice questions. So now we have to find the probability that if a question is selected, then it will be an easy question given that it is a multiple choice question. Now this is a question of conditional probability. Now how to solve it? Let's check out the solution of this. Let us say that E represents the event that an easy question is selected, and F represents the event that a multiple choice question is selected. So P of E would be the probability of selecting a easy question, and P of F would be the probability of selecting a multiple choice question. Now the sample space S is equal to 300 plus 200 plus 500 plus 400, that is equal to 1400 questions. So the sample space consists of, or the question bank consists of 1400 questions. P of F would be equal to 500 plus 400 equal to 900 divided by 1400. So 900 by 1400 would be the probability of selecting a multiple choice question. Similarly, the probability of selecting an easy question would be 300 plus 500 divided by 1400, and that is equal to 800 by 1400. Now, the probability of E intersection F, that is a easy multiple choice question, would be 500 by 1400, as we see that there are 500 easy multiple choice questions. Now we have to find the probability that an easy question is selected given that a multiple choice question has been selected. So P of E by F would be equal to the probability of E intersection F divided by the probability of F. This is the formula for conditional probability. Now this would be equal to 500 by 1400 divided by 900 by 1400, and that is equal to 5 by 9. Thus our final answer is 5 by 9. Now let us see one more solved example, and it says that a box of oranges is inspected by selecting 3 oranges without replacement. If all the 3 oranges are good, the box is approved for sale, otherwise it is rejected. Find the probability that a box containing 15 oranges, out of which 12 are good ones and 3 are bad ones, will be approved for sale. And it says that a box of oranges is inspected by selecting 3 oranges without replacement. So we select 3 oranges one by one and without replacement. If all these 3 oranges are good, then the box is approved for sale, otherwise it gets rejected. Now we have to find the probability that a box containing 15 oranges, out of which 12 are good ones and 3 are bad ones, will be approved for sale. So we have been given 12 good ones and 3 bad ones. That is, the box contains 12 good oranges and 3 bad oranges. Let us say that P of E represents the probability that the first orange being selected is a good one. P of F represents the second orange selected is good one, and P of G represents that third orange selected is also good one. Now we see that all the 3 events are independent of each other. Now we have to find P of E intersection F intersection G. That is, all the 3 events are happening. So the probability of E intersection F intersection G would be equal to P of E into P of F into P of G. Now P of E would be equal to 12 by 15. That is, we select 1 orange out of 12 good ones from a box of 15 oranges. So this would be equal to 12 by 15 into P of F. P of F would be 11 by 14 because we have already selected 1 orange from the good lot, and the total number of oranges also gets reduced because we are selecting an orange without replacement. Into P of G would be 10 by 13 because after selecting 2 good oranges, 10 good oranges are left and we select 1 good orange from those 10 oranges. Therefore this would be equal to 10 by 13, and this is important because this is without replacement. So this would be equal to 44 by 91. Thus the probability of the basket being approved is equal to 44 by 91. Now let's look at the most important theorem in probability, and that is the Bayes theorem or the inverse probability theorem. Bayes theorem gives the probability of occurrence of an event when the outcome of experiment is known. So here's a difference, that it tells us the probability of occurrence of an event given the final outcome of an experiment is known. So consider a sample space S. Let AI from 1 to n be the set of n mutually exclusive and exhaustive set of sample space S. So AI to an represents n mutually exclusive and exhaustive set of sample space S. Here we see that AI intersection AJ is equal to 5, where I comma j is greater or equal to 1 and less than equal to n. This is because these are mutually exclusive events, and the summation of probability of AI from I equal to 1 to n is equal to 1, and the sum of all events is equal to S. This is because S is the sample space, and the events AI, where I varies from 1 to n, represents the set of n mutually exclusive events and exhaustive set of sample spaces. So let us say that this is the sample space S. Your A1, A2, A3, A4, A5, A6, A7, A8 and so on up to AK represents the different events. Here we see that A1, A2, A3 and so on are all mutually exclusive events. That is, they do not have any common point of intersection. Also, all these events sum to the sample space S. Thus, we can say that all these events are mutually exclusive and exhaustive set of the sample space S. Now, consider event A. This yellow portion represents the event A. Now, this portion is A1 intersection A. This is A2 intersection A. This is A3 intersection A. This is A4 intersection A. This is A5 intersection A, and so on up to AK intersection A. Thus, all these portions represents the contribution of all these events in the formation of this event, which is capital A. So, A1 intersection A represents the contribution of the event A1 in A. Similarly, A2 intersection A represents the contribution of A2 in A, and so on up to AK intersection A. Now, let us say that A is the event of S which has already occurred. Then the conditional probability of occurrence of any one of the events, say AK, out of the events AI, where I varies from 1 to n, is probability of A of K by A equal to probability of AK intersection A divided by P of A. Now this is equal to P of AK into P of A by K divided by the probability of A. Now what is P of A? P of A is the contribution of all those events in the formation of A. Thus P of AK by A, which is this, that is the probability of A of K when A has occurred, is equal to the probability of AK into probability of A by AK, that is again the conditional probability, divided by the summation of P of AI into P of A by AI, where I varies from 1 to n. Now this is actually the probability of happening of A of K when A has occurred. This would be equal to the product of probability of A of K into the probability of happening of A when A of K has occurred, divided by the summation of, now this represents the contribution of all those events in the formation of the event A. Now this seems to be a bit complicated. We can understand this through an example. In a factory manufacturing bulbs, machines A, B and C manufacture 25%, 35% and 40% respectively of the total production. Of their outputs, 2%, 3% and 5% are defective bulbs. A bulb is drawn at random from the product and is found to be defective. What is the probability that it was manufactured by the machine C? Now, in this problem we have been given that there are 3 manufacturing machines A, B and C, and they manufacture 25%, 35% and 45% of the total production. Now, of their outputs it has been given that for A, 2% are defective, for B, 3% of the bulbs are defective, and for C, 5% of the bulbs are defective. Now any one bulb is drawn at random from the product, and when it has been drawn it is found to be defective. Now the end is known to us that the bulb is defective. Now from that we have to calculate the probability that it was manufactured by the machine C. So this is a typical case of Bayes theorem, and so let us say that A, B and C be the events that a bulb selected at random is manufactured respectively by the machines A, B and C. So A represents a bulb is manufactured by A, B represents a bulb is manufactured by B, and C represents a bulb is manufactured by C. So P of A would be equal to 25 by 100 because 25% of the bulbs are manufactured by A. P of B would be equal to 35 by 100 as 35% of the bulbs are manufactured by machine B, and similarly P of C would be equal to 40 by 100. Now let us say that D represents the event that the bulb selected at random is defective. So the probability of the bulb being defective, given that it was manufactured by A, is equal to 2 by 100 because 2% of the bulbs manufactured by A are defective. Similarly, P of D by B would be equal to 3 by 100 as 3% of the bulbs manufactured by B are defective, and P of D by C would be equal to 5 by 100 as this represents the probability that a bulb is defective when it is manufactured by C, and this is equal to 5%. Now we have to find the probability that the defective bulb was manufactured by C. So we are going to use the Bayes theorem for that, and that is P of C by D equal to P of C into P of D by C divided by P of A into P of D by A plus P of B into P of D by B plus P of C into P of D by C. This represents the probability of a bulb being defective, and this is the contribution of machine C in the bulb being defective. So the contribution of C divided by the probability of getting a bulb defective. Thus this is equal to 40 into 5 divided by 25 into 2 plus 35 into 3 plus 40 into 5. This would be equal to 200 by 355, and which is equal to 40 by 71. Thus 40 by 71 is the probability that the bulb which is found to be defective is from machine C. Thus 40 by 71 is the required answer. Let's see another solved example. It says that Rohit and his friends are going to visit Mount Fujiyama tomorrow. In the recent years, volcano has erupted only 5 days each year on an average. Fortunately, the scientist has predicted volcano eruption for tomorrow. When it actually erupts, the scientists correctly predicted eruption 90% of the time. Now, what is the probability that it will erupt on the day of Rohit's visit? So in this problem, it has been given that Rohit and some of his friends are going to Mount Fujiyama tomorrow. Now, in the recent years, volcano has erupted only 5 days each year on an average, and scientists have predicted a volcano eruption tomorrow. Also, it has been given that the scientists have correctly predicted the eruption 90% of the time. Now, we have to calculate the probability that the volcano will erupt on the day of Rohit's visit. So now how to solve this? Let's see the solution of this. The sample space is defined by two mutually exclusive events. Those events are that the volcano erupts, and the second is it does not erupt. So either it will erupt or it will not erupt. Additionally, a third event occurs when the scientists predict eruption. Now we consider one more event that the scientists have predicted eruption. So A1 would be it erupts on the Rohit's day of visit. Event A2 would be it does not erupt on Rohit's day of visit. And let us say that event B is scientist predicts eruption. Now P of A1, that is the volcano erupts on Rohit's day of visit, which is tomorrow, would be equal to 5 by 365, as it has been given that it erupts 5 days in a year. So this is equal to 0.014. Similarly, probability of A2, that is it does not erupt on Rohit's day of visit, would be equal to 360 by 365, because it does not erupt on the rest of the year. So that would be equal to 0.986. Now probability of B when A1 has taken place, that is the scientist predicts an eruption and the volcano has actually erupted, is equal to 0.9, because when it erupts, the scientist predicts eruption 90% of the time correctly. And probability of B by A2, that is the scientists have predicted the eruption but it does not occur. So this would be equal to 0.1, as this would be only 10% of the cases. So now we want to calculate the value of P of A1 by B, which is the volcano erupts on Rohit's day of visit and the scientists have predicted the eruption. So we get the value of P of A1 by B by the base formula, which is equal to P of A1 by B into P of A1 divided by P of A1 into P of B by A1 plus P of A2 into P of B by A2. So we put the values of these and get 0.014 into 0.9 divided by 0.014 into 0.9 plus 0.986 into 0.1, and which is equal to 0.11. So the final probability of eruption of volcano on Rohit's day of visit, given that the scientists have predicted the eruption of volcano, is equal to 0.111. The next topic is random variables and the probability distribution. Now to understand this, let us consider the simultaneous throw of two coins. Now we are throwing two coins simultaneously. Let us say that capital X denotes the number of heads. So S is the sample space, which is HH, HT, TH and TT. This is because it could be a head-head, it could be head-tail, it could be tail-head and it could be tail-tail on these two coins. Now X of HH, if we consider this event, then the number of heads is equal to 2, because X denotes the number of heads. Similarly for this event HT, the number of heads is equal to 1, because there is only one head here. For this event again the number of heads is equal to 1, and for this event we see that there is no head, and so X of TT would be equal to 0. Thus we can say that X assumes different values, that is 0, 1 and 2 in this particular case. So we can say that random variable is a real valued function X, which is defined over the sample space S. In this example the sample space was this, and so X was the random variable here. Similarly we can say that there can be more than one random variable defined over a sample space S. Now if I say that capital Y denotes the number of tails, so again Y would be a different real valued function, and so it is a random variable. Thus we can say that for the same sample space S, we can have more than one random variable. Now probability distribution of random variable. So a distribution in which the values of the random variable and the corresponding probabilities are given is called as the probability distribution of the random variable. So for each of the random variable we have a different probability given to us. So it is nothing but a distribution in which the values of the random variable are given and the corresponding probabilities are given. So this is called as probability distribution of the random variable. Let us suppose that a discrete variable x assumes the values x1, x2 and so on up to xn with the probabilities p1, p2 and so on up to pn respectively, where p1 plus p2 plus p3 and so on up to pn is equal to 1, and each of these probabilities lie between 0 and 1 for all I from 1 to n. So thus we say that x is a variable that assumes different values x1, x2, x3 and so on up to xn, and the corresponding probabilities would be p1, p2 and so on up to pn. Your p1 plus p2 plus p3 and so on up to pn would be equal to 1, and each of these probabilities would be greater or equal to 0 and less than equal to 1. So a typical example of a probability distribution table is this. You write the values that the random variable assumes, let us say that x1, x2, x3, x4, x5 and so on up to xn, and the corresponding probabilities are p1, p2, p3, p4, p5 and so on up to pn. So this represents a typical example of probability distribution. So let's try to see a solved example based on probability distribution. Two balls are drawn at random in succession without replacement from an urn containing 4 red balls and 6 black balls. Find the probabilities of all the possible outcomes. So in this problem we have been given that two balls are drawn at random in succession without replacement from an urn containing 4 red balls and 6 black balls. So we have to find the probabilities of all the outcomes, or the probability distribution. Let us say that x denotes the number of red balls in each of the outcome. So the possible outcomes could be red red, red black, black red and black black. So x, which is the random variable and which denotes the number of red balls in each of these outcomes, can be 2 in this case as there are 2 red balls, 1 in this case, 1 in this case and 0 in this case as there is no red ball. So x1 is equal to 2, x2 is equal to 1, x3 is equal to 1 and x4 is equal to 0. Now the probability of getting 2 red balls is p of x1, which is equal to 4 by 10 into 3 by 9, which is equal to 2 by 15. This happens because first initially we have got 4 red balls, and thus we see that there are 4 ways of selecting a red ball, divided by total number of ways is 10 because there are 10 balls, into 3 by 9. This is because now we have got only 3 red balls left and total number of balls is also 9. So the probability of picking up a red ball is 3 by 9. Thus the overall probability is equal to 2 by 15. Similarly, the probability of getting RB event is P of x2 equal to 4 by 10 into 6 by 9. Now in the second time we are picking up a black ball, and which are 6 in all. So this would be equal to 4 by 15. Similarly, the probability of B, that is black and red ball, is P of x3, which is equal to 6 by 10 into 4 by 9, which is equal to 4 by 15. And the probability of BB event is 6 by 10 into 5 by 9, which is equal to 1 by 3. And so these are the different probabilities of all the possible events. Let's see one more very interesting problem. It says that I throw a die and get $1 if it's showing 1, and get $2 if it's showing 2, and get $3 if it's showing 3, etc. What is the amount of money I can expect if I throw it 100 times? It says that if I throw a die, I'll get $1 if it is showing 1, I'll get $2 if it's showing 2, I'll get $3 if it's showing 3, and so on. What is the amount of money I can expect if I throw this die 100 times? So now this is the case of expected value. Now for one throw, the expected value is E of x equal to summation of x of I into p of xi. Your x is a random variable and p of xi is the corresponding probability of this random variable. Now this would be equal to, as this is the probability of occurrence of 1, and if 1 occurs then I'll be given $1, plus 2 times 1 by 6. Now this is the probability of 2 occurring, and I get $2 if I get a 2, plus 3 into 1 by 6. This is the probability of 3 appearing in the die, and this is the value which I am getting for it. Plus 4 into 1 by 6, again this is the probability of 4 appearing, and this is the value which I get when 4 appears. Plus 5 into 1 by 6, because this is the probability of 5 appearing, and this is the value which I get when 5 appears. And plus 6 into 1 by 6, again 1 by 6 is the probability of 6 appearing, and 6 is the value which I am getting for appearance of 6 on the die. So this is equal to 7 by 2, which is equal to 3.5. So when I throw a die once, then $3.5 is the value which I am expecting out of a single throw. Now for 100 throws, I would get 3.5 into 100, that is equal to $350. So the expected value if I throw the dice 100 times is equal to $350. The next part is the binomial distribution. Now if we consider n independent trials, then the probability of A happening, or the success of A, is equal to P, and the probability of A not happening, that is the failure of A, is equal to Q. Let us say that this is equal to P and this is equal to Q. Then P plus Q would be equal to 1, as these are mutually exclusive events, and so Q would be equal to 1 minus P. Now if we say that X is the number of times A occurs, that is X represents the number of times A happens, or it represents the success of A, then X is greater or equal to 0 and less than equal to n. Here n is the independent number of trials. So if we consider n independent number of trials, then the number of successes of A would be X, and this X lies between 0 and n, and P is the probability that A happens, and Q is the failure of A. Now X equal to R means that A occurs in R trials, and in the remaining n minus R trials it does not occur. So it may look like A up to R times it's happening, and in the remaining n minus R times it's not happening. So it should be represented by A complement. So A till R times and A complement to n minus R times represents one outcome in n trials. Now the trials are independent of each other, that is they do not influence each other. Hence the probability would be P into P into P up to R times into Q into Q into Q up to n minus R times, and this would be equal to P to the power of R into Q to the power of n minus R. Now we see that these could be arranged among themselves in NCR ways. Hence we can say that the probability of getting R successes or occurrence of A in R trials out of n independent trials is P of X equal to R equal to NCR into P to the power of R into Q to the power of n minus R. And this is the binomial distribution of the random variable X. Now X could be 1, 2, 3, 4 up to n. So in general, if A occurs R times, then X is equal to R, and so the probability distribution would be NCR into P to the power of R into Q to the power of n minus R. Here we should note that each of these n trials are independent of each other, and the probability of occurrence of A in one trial is P, and the non-occurrence of A is represented by Q. So P of X equal to R is given by NCR into P to the power of R into Q to the power of n minus R. Now let's see some of the very important results regarding the binomial distribution. The first is the probability of getting at least k successes is P of X greater or equal to k, and which is equal to the summation of NCR into P to the power of R into Q to the power of n minus R, where R varies from k to n. Thus, if we want to calculate the probability of at least k successes, here the random variable varies from k to n. So this would be equal to the summation of NCR into P to the power of R into Q to the power of n minus R, from R equal to k to n. The second is the probability of getting at most k successes is P of X less than equal to k, and this would be equal to summation of NCR into P to the power of R into Q to the power of n minus R, where R varies from 0 to k. So here for at most k successes, X would lie from 0 to k, and so it would be equal to summation of NCR into P to the power of R into Q to the power of n minus R, from R equal to 0 to k. And the third is the summation of NCR into P to the power of R into Q to the power of n minus R, from R equal to 0 to R equal to n, is equal to P plus Q to the power of n, and we know that P plus Q is equal to 1, so this would be equal to 1. So this would represent the probability of the sample space. Thus these are some of the important results regarding the binomial distribution. Now let's see a solved example. A manufacturer of metal pistons finds that on the average 12% of his pistons are rejected because they are either oversized or undersized. What is the probability that a batch of 10 pistons will contain, option number A is no more than 2 rejects, and second part is at least 2 rejects. So in this problem it has been given that a manufacturer finds that on an average 12% of his pistons are rejected. This is because either they are oversized or undersized. Now what we have to do is we have to calculate the probability that a batch of 10 pistons will contain, first part is no more than 2 rejects and the B part is at least 2 rejects. So this is a case of binomial distribution, and so let us say that X is equal to the number of rejected pistons. Now in this case success would mean rejection. So if a piston is rejected, it means the success, that is the happening of that particular event. Now you are given that N is equal to 10 as we have got 10 trials. P would be equal to 0.12 as 12% of the pistons are rejected. Q would be equal to 0.88. Now let us say that it has got no rejects. So X would be equal to 0, and thus P of X would be equal to NCX into P to the power of X into Q to the power of N minus X. Now we see that X is equal to 0 here. So this would be equal to 10C0 into 0.12 to the power of 0 into 0.88 to the power of 10. This would be equal to 0.2785. For one reject, X would be equal to 1. So P of X would be equal to 10C1 into 0.12 to the power of 1 into 0.88 to the power of 9. So this would be equal to 0.37977. Now let's consider 2 rejects. So X would be equal to 2, and hence P of X would be 10C2 into 0.12 square into 0.88 to the power of 8, and this would be equal to 0.23304. Now we have to calculate the probability of getting no more than 2 rejects. So P of X should be less than equal to 2, and hence we add all these probabilities, and thus 0.2785 plus 0.37977 plus 0.23304 would be equal to 0.89131. Thus the probability of getting no more than 2 rejects is equal to 0.89131. The second part is we have to calculate the probability of at least 2 rejects. So for at least 2 rejects, this would be equal to 1 minus P of X less than equal to 1. So now P of X less than equal to 1 would be P of X0 plus P of X1, that is no reject plus 1 reject, and hence this would be equal to 1 minus summation of 0.2785 plus 0.37977, and this is equal to 0.34173. Thus this is the final answer for the probability of at least 2 rejects. Now this was all about probability. Now let's try to solve a few examples that have been asked in IIT JEE. So this problem appeared in IIT JEE 1989, and it says that suppose the probability for A to win a game against B is 0.4. If A has the option of playing either a best of 3 games or a best of 5 games match against B, which option should he choose so that the probability of winning the match is higher? No game ends in a draw. So in this problem it has been given that the probability of A to win a game against B is 0.4. Now A has got 2 options, either he can go for best of 3 games or best of 5 games against B. Now which option he has to choose so that the probability of his winning the match is higher? Also given that no game ends in a draw. Let us take the case first as best of 3 games. Let us say that A and B play best of 3 games. Now in this case, if A has to win, then he should win 2 or more games against B. So number of wins should be greater than equal to 2. Now if X is the number of wins, then N is equal to 3, that is they are playing 3 games. P would be equal to 0.4 as his probability of winning a game against B is 0.4, and Q is equal to 0.6. This is the probability of B winning against A. Now the probability of X greater or equal to 2 is equal to the probability of X equal to 2 plus the probability of X equal to 3. Now this is equal to 3C2 into 0.4 square into 0.6 plus 3C3 into 0.4 cube into 0.6 to the power of 0. This is equal to 0.288 and this is equal to 0.064. When we add them up, we get 0.352. If A and B play best of 3 games, then the probability of A winning is equal to 0.352. Let's take case number 2, that is best of 5 games. Now if we say that X is the number of wins, then N is equal to 5. Here the number of games is equal to 5. So N is equal to 5. P is again 0.4 and Q is equal to 0.6. So for A to win, we should at least win 3 games. So P of x greater or equal to 3 would be equal to P of x equal to 3 plus P of x equal to 4 plus P of x equal to 5. For this we get 5c3 into 0.4 cube into 0.6 square plus 5c4 into 0.4 to the power 4 into 0.6 plus 5c5 into 0.4 to the power of 5. This is equal to 0.2304, this is equal to 0.0768, and this is equal to 0.1024. And when we add them up, we get 0.3174. Thus we see that P of x in the first case is greater than P of x in the second case. That is, the probability of A winning against B in best of 3 games is higher as compared to winning in the best of 5 games. Thus A should opt for best of 3 games, as this gives him a better chance of winning against B. Let's try to solve one more example. This problem appeared in IIT JEE in 1997, and it says that if P and Q are chosen randomly from the set 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10 with replacement, determine the probability that the roots of the equation x square plus px plus q equal to 0 are real. So in this problem we have been given that there is a set from 1 to 10 and we have to choose P and Q with replacement such that the roots of the equation x square plus px plus q equal to 0 are real. Now the given quadratic equation to us is x square plus px plus q equal to 0. Now we know that for roots to be real, the discriminant should be greater or equal to 0. That is, p square should be greater or equal to 4q. And for roots to be non-real, the condition is p square should be less than 4q. Now we know that the probability of roots to be real is equal to 1 minus the probability of roots to be non-real. So what we are going to do here is, we are going to try to find the probability of roots to be non-real and then subtract this probability from 1 to get the probability of roots to be real. Now we also know that P and Q belong to the set 1 to 10. So we choose different values of Q from 1 to 10 and correspondingly we find the values of P. Thus, when Q is equal to 1, P would be equal to 1, and so the number of pairs of P and Q would be 1. When Q is equal to 2, the values P can assume are 1 and 2, and thus the number of pairs become 2. For Q equal to 3, P can have values 1, 2 and 3, and so the number of pairs is equal to 3. When Q is equal to 4, P can have values 1, 2 and 3, and so the number of pairs are 3. When Q is equal to 5, P can have the values 1, 2, 3 and 4, and thus the number of pairs are 4. When Q is equal to 6, P can have the values 1, 2, 3 and 4, and hence the number of pairs is equal to 4. When Q is equal to 7, P can have 1, 2, 3, 4 and 5, and so number of pairs is equal to 5. When Q is equal to 8, P can have the values 1, 2, 3, 4 and 5, and hence again the number of pairs are 5. When Q is equal to 9, P can have the values 1, 2, 3, 4, 5, and the number of pairs become 5. And when Q is equal to 10, P can have 1, 2, 3, 4, 5 and 6, and so the number of pairs are equal to 6. Now, when we add all these number of pairs, we get the total number of such pairs for which roots are non-real are 38. Also we see that total number of possible pairs are 10 into 10, as Q can have 10 values and P can have 10 values, so such pairs are 100. Thus the probability that the roots are real is equal to 1 minus 38 by 100. This is the probability that roots are non-real, and so we get the probability as equal to 0.62. So the final probability that the roots are real is 0.62. Let's see another solved example, and this appeared in IIT JEE in 1989, and it says that an unbiased coin is tossed. If the result is a head, a pair of unbiased dice is rolled and the number obtained by adding the numbers on the two faces is noted. If the result is a tail, a card from a well-shuffled pack of 11 cards numbered from 2, 3, 4 up to 12 is noted. Now what is the probability that the noted number is either a 7 or a 8? So in this problem we have been given that an unbiased coin is tossed. If the result is a head, then a pair of unbiased dice is rolled and the number obtained by adding the numbers on the two faces is noted. And if the result of tossing of coin is a tail, then a card from a well shuffled pack of 11 cards numbered from 2 to 12 is noted. We have to calculate the probability that the noted number is either 7 or 8. So one can get a 7 or 8 either if it appears a head on the coin and then the sum of the two numbers on the dice result in 7 or 8, or it appears a tail on the coin and then a 7 or 8 number card is picked from a well shuffled pack of cards. So we can have two possibilities. Either a head appears and then the sum of the two numbers on the dice results in 7 or 8, or it can appear a tail on tossing of coin and then a card is drawn which could be a 7 or 8 number card. So let us say that even is the event of getting a 7, E2 is the event of getting an 8, H is the event of getting a head, and T is the event of getting a tail. So we define even as the event of getting a 7, E2 as the event of getting an 8, H the event of getting a head, and T the event of getting a tail. Now, thus from total probability we get P of even equal to P of H into P of even by H plus P of T into P of even by T. This represents the probability of getting a 7. This represents the probability of getting a head. This represents the probability of getting a 7 when a head has occurred. This represents the probability of getting a tail, and this represents the probability of getting a 7 when a tail occurs. Similarly, P of E2 would be P of H into P of E2 by H plus P of T into P of E2 by T. Again, this represents the probability of getting a head. This represents the probability of getting a 8 when a head occurs. This represents the probability of getting a tail, and this represents the probability of getting a 8 when a tail occurs. Now we know that P of H would be equal to P of T, and that is equal to 1 by 2. Either we can get a head or we can get a tail. Now, for getting a 7 on a dice, possible cases are 1, 6, 6, 1, 2, 5, 5, 2, 3, 4, and 4, 3. So P of even by H is equal to 6 by 36, which is equal to 1 by 6. The cases for getting a 7 numbered card is equal to 1. We have got 11 cards, and out of which there is only one card which is numbered 7. So P of even by T, that is the probability of getting a 7 when a tail has occurred, is equal to 1 by 11. Similarly, for getting a 8 on a dice, possible cases are 6, 2, 2, 6, 3, 5, 5, 3, and 4, 4. So we see that there are 5 cases. So P of E2 by H would be equal to 5 by 36. Similarly, cases for getting an 8 numbered card is equal to 1, as there is only one 8 numbered card from a pack of 11 cards. So P of E2 by T would be equal to 1 by 11. Thus P of even would be equal to, we put these values over here to get 1 by 2 into 1 by 6 plus 1 by 2 into 1 by 11. This is equal to 1 by 12 plus 1 by 22, and this is equal to 17 by 132. Thus the probability of getting a 7 is 17 by 132. Similarly, the probability of getting a 8 is equal to 1 by 2 into 5 by 6 plus 1 by 2 into 1 by 11, and that is equal to 91 by 729. Now we also see that even and E2 are mutually exclusive events, because if we get a 7 we cannot get a 8. Thus P of even or E2 is nothing but P of even union E2, and this is equal to P of even plus P of E2, which is 17 by 132 plus 91 by 792, and this is equal to 193 by 792. Thus the final probability of getting a 7 or a 8 is equal to 193 by 792. Now let's see the last solved problem, which appeared in IDJ 1991, and it says that in a test, an examinee either guesses or copies or knows the answer to a multiple choice question with 4 choices. The probability that he makes a guess is 1 by 3, and the probability that he copies the answer is 1 by 6. The probability that his answer is correct given that he copied it is 1 by 8. Find the probability that he knew the answer to the question given that he correctly answered it. Now in this problem we have been given that in a multiple choice question we have got 4 choices, and an examinee can either guess the answer, either he can copy the answer, or either he knows the answer to that multiple choice question. Now the probability that he makes a guess is 1 by 3. The probability that he copies the answer is 1 by 6. Also given to us is the probability that his answer is correct given that he copied it is 1 by 8. We have to find the probability that he knew the answer to the question given that he correctly answered it. Now this is an example where we use the Bayes theorem, but how? Let's check it out. Now this is any multiple choice question. Now there are 3 choices given to us. Either the examinee can guess it, the probability for which is equal to 1 by 3. Either he copies the answer and the probability for that is 1 by 6. Or the third option is he knows the answer to this question and the probability for which we do not know. So let us say that even represents the event that the examinee guesses the answer. E2 represents the event that the examinee copies the answer. E3 represents the event that the examinee knows the answer. And A represents that the examinee correctly answers a question. Also given to us is P of E1 equal to 1 by 3. P of E2 is equal to 1 by 6. So P of E3 would be equal to 1 minus 1 by 3 minus 1 by 6, which is equal to 1 by 2. As these are mutually exclusive events and they are also exhaustive events. So either the examinee can know the answer, either he can copy the answer, or either he can guess the answer. So that's why the probability of examinee knowing the answer would be equal to 1 minus 1 by 3 minus 1 by 6, and that would be equal to 1 by 2. Now the probability of the examinee correctly answering a question after guessing is 1 by 4. This is because we have got 4 options, out of which he makes a wild guess. If one of the option is correct, so the probability becomes 1 by 4. Thus P of A by even is equal to 1 by 4. This is the probability that he answers the question correctly, and the condition is he guesses it. So this would be equal to 1 by 4. Also given in the problem is P of A by E2, that is the probability of answering the question correctly when he has copied it, is equal to 1 by 8. Also we know that if the examinee knows the answer, then he would definitely answer it correct. He won't answer it wrong. So if any person knows the answer, he would definitely answer it correctly. Thus the probability of answering the question correctly when he knows the answer is equal to 1. We have to find P of E3 by A. That is, he knows the answer for which he answered it correctly. Again we are going to use the Bayes theorem for this. So P of E3 by A would be equal to P of E3 into P of A by E3 divided by P of E1 into P of A by E1 plus P of E2 into P of A by E2 plus P of E3 into P of A by E3. Thus this is equal to 1 by 2 into 1 divided by 1 by 3 into 1 by 4 plus 1 by 6 into 1 by 8 plus 1 by 2 into 1. So this is equal to 24 by 29. The probability that the examinee knew the answer given that he answered it correctly is equal to 24 by 29.